Hello and welcome everyone. I'm Shweta and today I'll be talking about more Penrose pseudo-inverse. We'll see the explanation, examples along with some code implementation. So here is the rough outline of what we're gonna see in this video. First of all, I'll give you a refresher on metric inverse. Then we'll see why are we even talking about this more Penrose pseudo-inverse. Then we'll explain what is more Penrose pseudo-inverse. After that, we'll see some really good example of how do we find pseudo-inverse. So, after that, we'll see real-world application of pseudo-inverse. And finally, we'll do the code implementation of pseudo-inverse. So let's get started with a refresher on inverse of matrices. So here we have a system of linear equation to solve. So basically, we all know that we can solve this equation using A inverse, right? We have this equation AX equals to B, and if we pre-multiply both sides with A inverse, then we simply get X as A inverse B. And that's how we can get our solution. But the catch here is that we are using A inverse to solve this system of equation. But A inverse do not exist for every matrix. It only exists for non-singular and square matrices, right? Why does inverse exist for only non-singular and square matrices? Here we're gonna see that. So one of the definition of matrices says that matrices are compact representation of linear transformations. So what we are trying to say is when we multiply a matrix A with the vector X, then what A is doing is it is simply transforming X to another vector B. And what A inverse do is when we multiply A inverse with vector B, it transform B back to the original A, X. So basically what A inverse is doing is it is undoing the transformation done by the matrix A. But the catch here is that not every transformation is undoable. For instance, think of a matrix or a transformation that takes us from 2D space to 3D space. So basically, it is adding one more dimension to the vector. Or think of a matrix that squishes things from 3D space onto a line. So it is reducing the dimension. These kind of the matrices we get from these kind of transformation are not invertible. Basically, these are the rectangular matrices. And the thing is, in real world problems, most of the matrices we deal with are not the square matrices, whose inverse is easy to find, but the rectangular matrices. Broadly, we come across with rectangular matrices in two types of linear system of equation. One of them is overdetermined system of equation and another one is underdetermined system of equation. So what is a overdetermined system of equation? Suppose we have a matrix A with dimensions m cross n, right? So in overdetermined system of equation, m is greater than n. Basically, the number of equation is more than the number of variables. And what about underdetermined system of equation? Here we have if A is a m cross n matrix, then n is greater than m. So basically here we have more number of variables or more number of columns than number of equation or the number of rows. So in both of the cases, we are getting a rectangular matrix, and we know it very well that inverse do not exist for rectangular matrices. But in order to solve this ax equals to y, we need to find a way to find A inverse. So here comes into the picture a pseudo inverse or more Penrose pseudo inverse. So to help us comes into the picture more Penrose pseudo inverse. So what it is? Basically, a pseudo inverse is of a matrix A is generalization of inverse of the inverse matrix, right? A pseudo inverse, it is represented by A with a plus like symbol at the top. So the most widely known type of matrix pseudo inverse is Penrose pseudo inverse. A common use of pseudo inverse is to compute the best fit or least square solution to a system of linear equation that lacks a unique solution. The pseudo inverse is defined and unique for all matrices whose entries are real or they can be complex numbers. Matrix inverse exists only for square matrices, right? But the real, as we discussed before, the real world data is not always square. Furthermore, real world data is not always consistent also. So to deal with this real world data, generalize inverse for rectangular matrices indeed. So the one of the way we can find a pseudo inverse also includes singular value decomposition that we are going to uh, see further. Broadly, we'll be discussing three cases of rectangular matrices. First one is when A is a M cross N matrix and columns of A are linearly independent and the rank of matrix A is equals to N, that is equals to the number of columns. Second case we are going to discuss is when A is a M cross N matrix and rows of A are linearly independent. And the rank of matrix A is equals to number of rows of matrix A, that is equals to M. Third case is we are going to discuss is the special one when A is a M cross N matrix and rank of A is less than M and all less than M, that is less than the number of rows, and rank of A is also less than number of columns, that is N. So the first matrix is called a full column rank matrix. And the second type is known as full row rank matrix. And third one is simply called rank deficient matrix. So we're gonna see how we can define a pseudo inverse for all these three cases. So let's begin with our first case, that is when the matrix is full column rank matrix. That is, the rank of matrix is equals to n when the dimension of matrix are m cross n. So also the columns of A are linearly independent. So for this case, we define pseudo inverse as A transpose A whole inverse A transpose. We call this inverse as left pseudo inverse. We call it this left pseudo inverse because when we multiply this inverse to the left of A, then we get identity matrix. We can write it another way, that is A transpose A inverse, and we can take these two together. And here we get an identity matrix. This is supposed to be a square matrix and a square and an inverted invertible matrix, as when we multiply, as we know A is a rectangular matrix here, and when we multiply uh, a rectangular matrix with its transpose, we get the square matrix. So let's move on to our second case, where our matrix A is a full row rank matrix, or simply where the rows of A are linearly independent and the rank of A is equals to m, that is equals to the number of rows in A. So for this case, we define pseudo inverse as A transpose into A into A transpose whole inverse, right? We call this as right pseudo inverse because when we multiply, as we saw previously in the case of left inverse, here we multiply this inverse to the right of the matrix A, and we get a identity matrix simply. That is why we called it as right pseudo inverse. So now we will move towards our third case. So here is our third case, where A is M cross N matrix and rank of A is less than M and rank of A is less than N. So this is a case of rank deficient matrix. Here the matrix A is not a full rank matrix. So in this case, we take help of singular value decomposition to define the pseudo inverse. Just for a recap, in singular value decomposition, we decompose the matrix A into three components. First one is U, that is orthogonal matrix. Second one is sigma, that is diagonal matrix, and third one is B transpose, that is also an orthogonal matrix. So to find the pseudo inverse, what we're gonna do is we're gonna simply take the inverse of the SVD. So just to simplify it, when we take inverse, we have got V transpose inverse, sigma inverse, U inverse, and V transpose inverse is simply nothing, simply just V. Then sigma inverse is just simply sigma inverse, and U inverse is simply U transpose. U inverse is equals to U transpose because we saw that U is a orthogonal matrix, and the transpose of orthogonal matrix is equals to its inverse. Here, for inverting the diagonal matrix, that is sigma, that is a diagonal matrix, we just take the reciprocal of the values of its diagonal values. So now we have seen that how we define pseudo inverse for all the three cases. Now we're going to see some examples and see how if we can find inverse using these example, how we can find pseudo inverse using these formulas. Begin with our examples. Here is our first example. We have a matrix A. Uh, we have a matrix A. So here we can see that the rank of the matrix is 2. And since the rank of the matrix is 2 and the number of columns is also 2, it is visible that the matrix is a column rank matrix. And we can also see that the columns of the A are linearly independent. So in this case, we are gonna use to find the pseudo inverse of matrix A, we are gonna use the formula A pseudo inverse equals to A transpose A whole inverse A transpose, as we saw in the previous slides. Moving to A transpose A, that is simply we are multiplying transpose of A with A, and we get this square matrix. Next, what we're gonna do is we're gonna find the determinant of this A transpose A, that is simply nothing, 36 minus 9, that is 27. Then next we're going to find inverse of A transpose A. Here we have a simple 2 cross 2 matrix, and we can simply find the inverse using the formula AD minus BC D minus B minus CA. And here we have found this A transpose A inverse. So next we simply multiply this A transpose A inverse to A transpose to get the pseudo inverse as was our formula. And this is nothing but simple multiplication. And here we are with our answer, that is the pseudo inverse of the rectangular matrix, or I would say left inverse. See, this was a very simple example. I encourage you to try the next example on your own and do the calculation. So moving forward, here we have another question where we have this matrix A. We can see that the rank of this matrix is equals to 2. That is equals to the rank of this matrix is equals to 2, and that is equals to the row number of rows of this column. So here we have the rows of the matrix linearly independent, and we have full row rank matrix. So in this case, we will use the defined formula, that is for pseudo inverse A transpose into A transpose whole inverse, right? So moving forward with the solution. First of all, we will here we have A and A transpose. We can simply find A into A transpose, just simple multiplication. Here we came with a 2 cross 2 matrix. Now, furthermore, we're gonna find determinant of this matrix, that is also simple. Then again we're gonna find inverse of A into A transpose, simply again using the formula. Then to find the pseudo inverse, we pre-multiply A transpose to the matrix we just calculated, A into A transpose whole inverse, and here we are with our answer. So this is how we found a right inverse of a matrix. Next, we're gonna do one more example. Moving toward our third example, we here have A equals to this matrix, and we can see that this is a rectangular matrix, and these two columns are linearly dependent. Also, the rows are linearly dependent. So the rank of this matrix A is 1. So in this case, rank of matrix is less than the number of rows, also less than the number of columns. So here we come to our third case, that is rank deficient matrix. So in this case, we will be using our singular value decomposition method for finding the pseudo inverse of the matrix A. So to calculate the pseudo inverse of A using SVD, we first need to calculate the matrix V sigma inverse U transpose. Uh, for that, first we need to calculate V, U, sigma, and V transpose. First of all, we will compute A transpose A. That is nothing but a simple multiplication, and we get this matrix. Then after this, with the simple procedure, we mm, subtract lambda from the diagonal elements and keeping the rest of the elements same. That is a simple procedure that we know already. Then we will solve this determinant of this matrix, and then we can find these eigenvalues for this matrix. And here are the eigenvectors, respective eigenvectors for these corresponding to these eigenvalues. Next, what we are going to do is we're going to find the singular values for the A, that are nothing but simply the under root of the eigenvalues. And here are our normalized eigenvectors. Next, we're going to find V, that is simply the eigenvector, normalized eigenvector, and sigma, that is simply the non-zero eigenvalue, singular values, non-zero singular values. Uh, that is simply a diagonal matrix with non-zero singular values as its diagonal elements. From this, we can find our u1 using 1 upon sigma AV1 and u2 as this. We can when now we have u1 and u2, and from this we can form our u. Now to find the pseudo inverse, we can simply multiply the matrices that we found out in the previous steps. That is, we multiply V, sigma plus or and U transpose, and just simply multiplying these three matrices will give us our pseudo inverse for the rank deficient matrix. So here, what we learned was finding the pseudo inverse for three cases. First one was the full column rank matrix. Second one was the full row rank matrix, and third one was the rank deficient matrix, for which we use the SVD method. Okay. Now next we're gonna see what we are seeing is the summary of what we learned. If we have a square matrix where m is equals to n equals to rank of the matrix, then the pseudo inverse is simply A inverse. The second case is when m is greater than n and n is rank of the matrix is equals to n, that is a column rank matrix. Then the pseudo inverse is defined as left inverse, that is given by this. And third one is the wide matrix, or I would rather say column row rank matrix. For that we have pseudo inverse as right inverse, that is defined by this formula. So next we're gonna see is an example of where we'll be solving the So next we are gonna solve a system of linear equation. Here we have our two equations. First of all, let's write them into matrix vector notation. And here is our A, X, and B. And our goal is to find a vector X. So here you can see that the rank of the matrix A is 1, since the columns of the matrix are linearly dependent. Also, the rows of the matrix are linearly dependent. So this is our, we can see that this is our third case where we're going to find the pseudo inverse using the SVD method. So simply we have our pseudo inverse as this. So we will use our simple method and we will calculate the eigenvalues of the matrix A transpose A, and those are 50 and 0. Then next step is we'll find the singular value of matrix A and matrix A, that are sigma 1 and sigma 2 is 0. I encourage you to solve these, do the calculation on your own and check this out. And here we have our sigma, V, and U. Next, we will simply calculate the we will calculate A, and we take A inverse, and here we have our pseudo inverse, And now to find x, we can simply multiply the pseudo inverse with the vector b, and we get our vector x. So these were some examples of finding pseudo inverse and using pseudo inverse to solve a system of linear equation. Next, so let's move on towards the application of more Penrose pseudo inverse. So here I've listed some of the application. Pseudo inverse have been used in these fields for quite a long time for now. Some of the fields common fields that use pseudo inverse are graphics. In graphics, specifically talking image recognition, image restoration, data compression, etc., etc. Next is robotics. Pseudo inverse has got various application in the field of robotics. Next is statics, as well as the obviously different branches of engineering have use of mathematics uh, and pseudo inverse. Next, what we're gonna do is hands-on implementation of more Penrose inverse. Now we're gonna see some implementation of what we have been talking about. So it's gonna be a quick go through of this code, and I'll be providing the link to this code. So first of all, we'll start by importing the libraries. We are importing NumPy, Matplotlib, and Seaborn. Okay, so we're gonna see through this code using these three system of linear equation consisting of three equations, right? First, we have this ax equals to y, and first of all, we're gonna convert it into the matrix vector form. Here is the matrix vector form. Now, next, we're gonna define our a, that is a numpy array, right? I have hard coded it. See, it's a. I've already run this notebook, but let's see it. So for we're gonna first find the singular value decomposition of matrix A. Okay, so here to find the singular value decomposition, I'm using this function and we dot lin algebra dot svd. So basically, svd is there is an inbuilt function in NumPy linear algebra library that we can use to find the components of singular value decomposition. So what this function gives us is first is u. U is the left one matrix that we get in the singular value decomposition. It's a orthogonal matrix. Second thing is V transpose. That is the right one matrix that we get in singular value decomposition. Next one is D. D consists of the singular values of A. Okay. So let's get, we will use numpy dot die and diag to find, to get the diagonal matrix. Here is our diagonal matrix. Now we know we have to get A, we're gonna multiply U, V, U, D, and V transpose. So we're gonna multiply to multiply this the dimension of D must be uh, uh, must be same as these, right? So let's get the dimension of D right, and here is how we get the dimension of D right. Next, what we're gonna do is we're gonna check if all these component that we got from the SVD function and some tweaking, uh, are we getting the same matrix? Yes, we definitely are getting the same matrix when we use this np dot dot function to get the dot product of to get the dot product to get the dot product of all those three components. Yes, we have the same matrix, right? So the function gives us the right components. Next, what we're gonna do is we're gonna find the more Penrose pseudo inverse. So here is our A, here is our V transpose, but according to the formula in the slides, we need V. So to get V, we will use the V T dot T function, and we will transpose V transpose, and we will get V, right? Here is the transpose V transpose, and that is V. Next, we're gonna create D plus that we first need to invert the non-zero values of D, right? Here we have D. So let's see what we'll get on inverting these value, or simply reciprocal of these value. Here is the reciprocal of these values. First of all, we have reciprocal of this value. Then here is the reciprocal of this value, but we need not to do the all this. We can simply use the inverse function, that is a built-in function in NumPy linear algebra library. And here we have our D plus matrix, but the D plus matrix must have the same dimensions as A transpose. So we're gonna get the dimension right, and this these lines of code will get the dimension right for the D transpose, for the D plus. Now we have everything that we need to calculate the pseudo inverse using that formula, and we simply do the dot product of these values, and here is our array, that is the pseudo inverse of A. So it was fun doing all of this, but to make things easy, we already have a built-in function in NumPy library, that is PINV, in which you can pass the matrix and you can get the pseudo inverse in simply one step. So here is the answer that we have gotten from using PINV. P stand for pseudo, INV stand for inverse, and we can clearly see that this function and this function, this array and this array are same. So we get same answers. Next, so here we have gotten our inverse. So next what we're gonna do is we're gonna just use these value to find the value of x. We can simply multiply y with a pseudo inverse of a, and here are our values for a. So this was it, guys. Thank you very much.